we have the pleasure to have as the first lecturer for the seminar of this year series, Professor Delsing from Chalmers University. Delsing has made his studies in Lund and in Göteborg, and he's a professor now in Chalmers, and he's a member of the Swedish Academy of Sciences, and he's well known for his work with superconductors, and in particular now with this field of artificial atoms and interacting with radio frequencies and with phonons in solids. And this field has a strong relationship with the domain of cavity QED, which I've been discussing in my lectures. And these kind of artificial atoms are even bigger than Rydberg atoms, and so they are very, very strongly coupled to radiation in particular. And I remember the beautiful experiments that I visited a couple of years ago in Chalmers, where one can demonstrate that in one dimension, effects which have been very difficult to observe in optics are observed with very clearly when atoms interact with one dimension radiation, such as the optical theorem, the absorption, the cross-section for absorption of and forward propagation of light were very beautifully demonstrated. So I'm sure that we will hear a little bit about that, but maybe about new developments, and I'm glad to give you the floor for your lecture.
So thank you very much. I'm sorry I can't give this talk in French, so I will stick to English. What I would like to tell you today is about propagating photons and phonons and how they can interact with really big atoms. And the atoms I'm going to talk about are artificial atoms. And we make them from superconducting circuits. And I will come back to that and tell you how we make them and how they work. So this is the outline of my talk. I will start with an introduction telling you about the tools, the transmission lines, and the artificial atoms that we work with. I will discuss scattering of light on atoms. In my case, the light has very low frequency, so it's microwaves. So 5 orders of magnitude lower frequencies than for optical light. But nevertheless, these are electromagnetic waves, and the field can be quantized, and we can discuss it in the same terms as we discuss light. So this is done at very low temperatures because we want the thermal fluctuations to be small compared to the photon energy. And it's done on a chip. So you can say that this is quantum optics on chip, but at very low temperatures and at very low frequencies. So then I will tell you 2 stories. One story is about photons and how you can scatter microwave photons on these artificial atoms. In all the cases, I will show you 3 examples here. And in all cases, I will work in just one dimension, which makes things simple. And the second part of the talk, which is actually the bigger part of the talk, is a new development where we can do very similar things with propagating phonons, so lattice vibrations using surface acoustic waves. So I will show you how we can also use the phonon degree of freedom to interact with these superconducting artificial atoms. And what I'm talking about is essentially described in these papers here. So let me start by telling you about the transmission lines. So we want to work in one dimension, so we have to guide the photons and the phonons through one dimension. And on a chip, this is very easily done in a coplanar waveguide, where the center, where you apply voltage to the center strip, and then you ground the outside electrode. So these are ground planes. So there's an electric field between the center conductor and the ground plane, and you have a propagating wave in one dimension on the chip here. So you can guide the photons along that 1D line. You can do something very similar with surface acoustic waves. And so you can generate with this thing here, which is called an interdigitated transducer, and I will come back to that. But that can generate surface acoustic waves that can be then transported on chip, and in a collimated beam, much like a laser beam, it doesn't really diffract. So that it can move a long distance over the chip and then be picked up by another interdigitated transducer. So in both cases, I will talk about frequencies which are about 5 gigahertz. And the speed of light is, of course, much, much larger than the speed of sound. So the speed of light is, of course, renormalized because we have a dielectric constant of our substrate, so it's a bit slower than speed of light in vacuum. But you see here that the wavelength is about 25 millimeters. For the phonons, the speed of sound is almost 5 orders of magnitude lower than for light, and therefore the wavelengths are also correspondingly shorter. Now, the atoms that we are using looks like this. This is 2 superconducting electrodes, and there's 2 Josephson junctions in the middle here. And to first order, we can think of this as just a harmonic oscillator. So here you have the transmission line, which couples capacitively to this LC oscillator, and you can see that there's a finger capacitance, and the Josephson junction essentially makes up an inductance. There's a Josephson inductance. And of course, the energy spectrum of a harmonic oscillator is equidistant. And so in a harmonic oscillator, you cannot really address individual levels. So what you need to make an atom or an artificial atom is some nonlinearity. And we have the nonlinearity built into the Josephson junction. So if you use the Josephson junction here instead of a pure inductance, you actually get an anharmonic spectrum. And in this way, this acts precisely like an atom. We can address individual levels here. The transitions have all different energies, and therefore we can address the levels individually. So this is the atom that we're going to work with. To say a little bit more in detail about this particular type of artificial atom that I'm going to talk about, this is called a transmon qubit. And I will use both the word qubit here, which is when you only have 2 levels, but of course these systems have several more levels, and if you use those, it's more like an artificial atom. And so this system here has actually 2 Josephson junctions in parallel. They enclose a loop here, and if you change the magnetic flux through this loop, you can change the effective Josephson energy, and therefore you can also change this nonlinear inductance. So the Hamiltonian for this system is very simple. It has 2 terms. It has a charging energy, and it has a Josephson coupling energy. And so, in fact, if this had been a quadratic function, this had been just a harmonic oscillator. But since we have a cosine here, this becomes an anharmonic oscillator. And you can relate this, so you know, for an ordinary harmonic oscillator, we have P and Q as the conjugate variables. Here, it's the phase and the charge which are conjugate variables, which obey this commutation relation. And so we can quantize this system, and we can calculate the energy spectrum, and this gives the energy spectrum then where EJ is the Josephson coupling energy and EC is the charging energy. And the nice thing is that we can tailor the energy spectrum of this atom. So we can give it precisely the energy structure that we would like to. So this is the one we will use, and we will scatter light of this artificial atom. There has been a number of experiments in this, but using these artificial atoms in cavities has been down now for 10 years. And so it's a bit of a new development to do this not in a cavity, but in an open transmission line. And there's been a number of experiments that you see here. The first people who did this was people at NEC in Japan, and they used a different kind of qubit. They used a flux qubit. And they could see a number of atomic physics things. So they could see electromagnetically induced transparency. They could see the Mollo triplet and nonlinear reflection from an atom. We at Chalmers have used instead the transmon qubit. We have essentially been able to see the same things here, and we have used it to demonstrate a number of different things. And essentially, these are the things that I will be talking about. Recently, there's also been an experiment from Andreas Wallraff's group in Zurich, where he has started to put more of these atoms together in an open transmission line and looked at interactions between these atoms. Let's model our system. So here you see this atom, and then we have a transmission line. We can display that as a circuit in this way. So here we have our atom, and then we have a transmission line on each side, which we can model as an infinite set of capacitors and inductors. And so we can quantize the system, and we can also calculate what is the reflection coefficient if we send down a photon coming in here, how much gets reflected and how much gets transmitted. And that's this expression here, which I will guide you through. So what you see here is this is the detuning. So the difference between the frequency you're sending in and the 0-1 frequency of your atom. Here, this is the decoherence rate. So this is the rate at which the atom loses coherence. And this big omega here is just the Rabi frequency of the radiation you're sending in. So it's the strength of the radiation. So in fact, if you go to low power, so this one can be neglected, and you go on resonance, so delta omega becomes 0, this becomes a very simple expression. So you see this, you just get this here, which is the relaxation rate, and here is the relaxation rate and the pure dephasing. So if the pure dephasing is 0, you in fact have a full reflection of your photons. So this simply becomes -1 here. So theory tells you that if you shine light on an atom, everything should be reflected if the power is low enough so that the photons arrive one by one. You can think of this, if you think of this in 2 dimensions, if you have something which scatters light here, and then you have an incoming wave, and then you simply superimpose those, you can see here that you have a destructive interference in the forward direction. If you compress this into 1 dimension, this becomes perfect, so that essentially the extinction in the forward direction is complete, and the reflection is also complete. So everything gets reflected, and nothing becomes transmitted. Of course, this is something that you can try to do also with ordinary atoms or molecules and laser light, but it's very hard to focus a laser on a single atom or a single molecule. The best people have been able to do is 12% of reflection from real atoms or molecules. So let's see how we can do here. So this is the measurement setup that we're using. So down here is our atom, and this is our transmission line. We're sending down radiation, so microwaves, and we have to attend, so we're sending it from room temperature, and we want to have it down to something which is colder than 50 millikelvin. So we have to attenuate it a lot on the way down. When it comes here, it can get reflected, and then it will go up through these circulators here, and we can detect it with these amplifiers. And out here, we get the signal of the reflection. Whatever is transmitted will go this way instead, and we will come up through an identical chain, and here we get a signal that is the transmission. We can also send a signal from this other side here and check that everything is symmetric, and it is. And in addition, we can also use this line here to address other levels than just the two lowest energy levels, 0, 1. We can specifically we can address the 1-2 transition, and that we're going to use in the future of this excursion. So this is how we measure. And here is the result of the transmission as a function of incoming power. So you can see that this is very low powers. So this is of the order of femtowatts down on this end here. And what you can see is the transmission is very, very low for both of these two samples. So the first one we tried was this red one here, and you can see that there's about 10% coming through in transmission. But we could engineer that sample, or we could engineer a new sample where we actually have an extinction of 99.6%. And that should be then compared to the 12% you get from real atoms. But what you see more here is that if you go up in power, the transmission actually goes up, and it goes up all the way to 1. So this is a very nonlinear transmission, so that when photons are coming one at a time, they all get reflected. But if they are coming many at a time, the atom can only deal with one at a time, and essentially all the others ones will pass by. So this is a very nonlinear system. And you can see it's because we have a system that we can engineer that we could change the pure dephasing here from 18 megahertz to 2 megahertz by just changing the parameters of the system. And that allowed us then to make something that had 99.6% extinction rather than 90% extinction. Now, if you drive the two lowest levels relatively hard, you will create Rabi dressing of these levels here. And that will lead to a Mallow triplet that we can observe here in transmission. So if we measure the transmission and we drive it really hard, when the Rabi frequency becomes bigger than the line width, we can see that we have these three lines here coming out. So this is the Mallow triplet of an artificial atom. We can also do this. We can use two tones at the same time. And here we're sending in a strong signal on the 1-2 transition. So we're Rabi dressing these two states. And that means that we have here now the original frequency is no longer in resonance, but we have a red detuned and a blue detuned line. And that's what you see here. So here we have control power on the x-axis, and we have frequency on the y-axis. And you can see that here, red, we have good reflection. Blue is then full transmission. And then if we go from here and apply high power, you see that this splits up here, and this is the Outler-Towns splitting. And what you see here is that we have actually very good transmission out here at the same frequency as where we have reflection here. And so this is essentially electromagnetically induced transparency. We create transparency by shining on a controlled tone. And this we can use to make a photon router. And so that's the next slide here. So the idea is the following. We have our transmon qubit here. We send in a signal, and it just bounces, it gets reflected and comes out here. But if from this side we send in a control pulse, that will make the system transparent. So this goes in at the 1-2 frequency. Then the signal that comes in from this side just goes through and comes out here. So we can make the photon coming in go to output 1 or output 2, depending on whether we send in a control signal. So let's see how that works. So here is data. We send in a continuous wave on the 0-1 frequency, and then we send in a strong tone on the 1-2. And what you see here is the on-off ratio, and you can see that for sample 1, which wasn't perfect, you can see that we still have a 90% on-off ratio. And this is done over a microsecond. Sample number 2 had an on-off ratio of 99%. So it's really a good router. Now you can ask yourself, well, how fast can you do this? And that's shown in this next slide here. So here we have the blue here, which is when you have full transmission. And the red is when you have no transmission. And then you see that we decrease the pulse length. And even though we decrease it from 1 microsecond to 50 nanoseconds, we don't really lose any contrast. And in fact, we can do this also with a 10 nanosecond pulse. And if we adjust our timing right so that we can actually sample when it hits the peak here, we don't lose any contrast even with a 10 nanosecond pulse. Theoretically, we would expect that this would fall off when we go above this relaxation rate or this coupling rate, which is 2 nanoseconds in this case. Okay, so that was the photon router. The next thing I'm going to show is creating non-classical states. So you know, if you have a source of radiation here, you can test the properties of this, or the statistics of the radiation, by using a beam splitter and 2 photon counters. And then you can construct this second-order correlation function. And essentially, if you have a source of single photons, only one of these will click at a time. And this relates to the Hanbury-Brown Twiss experiments. But what's important here is the second-order correlation function. And in microwaves, we don't have single photon counters. And the reason is simply that the energy of each photon is 5 orders of magnitude smaller than for optical frequencies. So it's actually very hard to detect a single microwave photon. But what we do have is linear amplifiers, so we can amplify the signal and measure the voltage. And that, in fact, gives us the same information. Now, if you classify different kinds of light in terms of this second-order correlation function, if you just have thermal light, the photons will tend to bunch because they are bosons. And then you will have a second-order correlation function that will go up to 2 here at 0 time delay. If you have a coherent source like a laser, or in our case, a microwave source, a coherent microwave source, your G2 is just 1. And if you have a single photon source, you're going to have anti-bunching. The photons are never going to arrive at the same time in the 2 detectors. Then you're going to have anti-bunching here, which is shown as a G2 which is less than 1. And so we have calibrated our system. So this is a measurement of G2 for thermal microwaves, the red and the blue. There are no free fitting parameters, and you can see that it goes precisely up to 2. There's a slight deviation here, but we believe that this is not because of our measurement. This is simply because the filters we put in were not exactly 10 megahertz and 2 megahertz. So the width of this here depends on the filtering and the bandwidth that you're investigating. If you put in coherent light, you see just a 1 here with very little ripple. So now we change our measurement setup slightly. So we still have 2 measurement chains here, and we can send in signals from 2 ways. But instead of looking at either side of the atom, we now put everything on one side, but we put here a microwave device which is called a hybrid, and that acts precisely like a beam splitter. So whatever comes, so if we send something in here and it gets reflected, it comes back this way, and it's beam splitted between those two, and then we can measure correlations between the 2 voltages that come out. And so we can construct this second-order correlation function by measuring this thing here, where these p's here are the powers that come out. So it's the voltage square. Okay, so we do that. And what we see is that the radiation that gets reflected really has anti-bunching. So you see that this is 1 here, and then it goes down to about 0.5, and it comes back up again. And of course, you can ask yourself, why isn't this 0? And we understand that. We've done a lot of theory to understand why is this anti-bunching not 0. And the reason is really imperfections in our measurement setup. That we have a trigger jitter, which adds a little bit. We have a non-zero temperature. We have a bandwidth of our filters. And we have circulators which are not perfect. And those things together makes this signal rather 50–60% than 0. Let me add here that you see that this is a rather noisy signal, and this is because this takes a very long time to do. We have to overcome the noise of our linear amplifiers. So each amplifier adds of the order of 40 noise photons, and we have to average that out. So in fact, a trace like this took 17 hours to measure. So you also need to have stability of your amplifiers then to do this. But it's possible to do. And what you see is that this is a very simple way of making non-classical radiation. You simply send in a coherent signal, let it bounce on the atom, and then you have a non-classical signal. Then the third example that I'm going to show you is that you can also make interaction between photons using these artificial atoms. As you know, it's very hard to make photons interact. You need to let them interact via matter in some way. So what we do here is we have our artificial atom, and we send in 2 signals here, one probe and one control. And the probe is almost resonant with the 0–1 transition, and the control is resonant with the 1–2 transition. And the idea here is that we have signals here at the single photon level in both channels, and we measure then the phase of one signal, the probe, when the control comes in, and see how much does the phase of this signal change when we have an incoming control field or an incoming control photon. And so we can measure this as the phase, as a function of the number of incoming photons. So 1 here means that there's 1 photon coming per interaction time, or coupling time. And what you see is that we have a very large phase. We have, for 2 different samples, we have 10 degrees per sample, or we have 20 degrees per photon, I should say. And this should be compared to if you have a nonlinear medium in quantum optics and you send down, the cross-Kerr effect there is only like 10 to the minus 4 degrees or so per atom. So here we have an extremely strong nonlinearity because of these Josephson junctions, and we get a very strong interaction. So that's really the benefit of these systems, is that they have a very strong interaction. And of course, partly because they're very large, their dipole moment is very large, even bigger than for Rydberg atoms. So now I'm going to shift gears a little bit and tell you about propagating phonons instead. And there has been a number of recent developments where people have been able to look at mechanical motion at the quantum level. People have used these piezoelectric bulk crystals and been able to couple them to superconducting qubits, and they've cooled them down and actually observed the quantum motion of these things. Here is essentially a drum which makes up a capacitor coupled to a resonator. And here is also a capacitive mechanical system coupled to a transmon qubit, as you can see. And these have managed to reach the quantum level so that the phonon degree of freedom is also in its ground state. But these are all localized mechanical modes. So, you know, this looks like a drum. So you can say that this is quantizing the musical instruments. What I would like to talk about now is how we quantize the music itself. So the propagating sound waves rather than the musical instruments. And the thing we use for that is surface acoustic waves. And this is an animation of a surface acoustic wave. You can see that it resembles ripples on a pond, on water. There's a distance in here where you have motion of the atoms. And the depth of that is roughly 1 wavelength. So in our case, 600 nanometers. And so this is the mechanical mode that we're going to use. So how do you generate and detect surface acoustic waves? Well, you do this on a piezoelectric substrate. And there are different kinds. You can use gallium arsenide or quartz or lithium niobate, for instance. We have used gallium arsenide, which is a relatively weak piezoelectric material. And we have used these so-called IDTs, interdigitated transducers, which looks like this. You have a finger capacitance, and when you apply a voltage, you get an electric field on the substrate, which then induces strain. And if you do that repeatedly, you will create a mechanical wave that will travel on the surface of the chip. So very much like this here. If the wave comes into an IDT like this, you can also convert back. So you can detect the incoming wave here and convert it back to the electromagnetic domain, and then listen to the waves that are coming in. So this is something that we will do. So this IDT here is an important device because it converts between photons and phonons, and that is what we're going to use. Now, in the first experiment that I will show you, we were at a little bit lower frequency, so at 1 gigahertz. But here we had an interdigitated transducer here, and we had another here. This one was shorted, so essentially it just reflects all the surface acoustic waves. This one was hooked up to a microwave source, so this one we can feed with microwaves, so we can generate a surface acoustic wave that goes both this way and that way. And the one we're interested in is the one that's going upwards here. And so we can sort of make the surface acoustic waves bounce here back and forth between those two mirrors. So essentially we have a small cavity for surface acoustic waves. What we have here is a single electron transistor, and that's an extremely charge sensitive device that can sense charge which is even less than a single electron. Displacement charges down to microelectrons can be sensed with a single electron transistor. And so you see the wave that comes here has positive charge in the here, and there is negative charge here. So with this SET here, we should be able to detect that charge. So what we use is a radio frequency single electron transistor, and I will not really go into detail about that. What you need to know for this experiment is just that it's a very sensitive charge detector. It can detect charge that comes in on this gate here, but it can also then detect charge that is induced on the surface. So you see the total charge is seeing comes partly from the voltage, but it also comes from the strain that is induced in the substrate. And you see this is the piezo constant here, and this is the area of the SET island. So the charge here can be sensed by the single electron transistor. And the single electron transistor has a periodic dependence. So the output signal here depends periodically on the gate charge. Now, if you add a surface acoustic wave with a certain amplitude here, you see that you will actually average over more than one period here. So in fact, you can have a sign change here if you average for, say, 1.5 period. If you plot this here as a function of still gate charge on the x-axis, but then as increasing power of surface acoustic wave here, you can see this checkerboard pattern here. And I won't go into detail, but what you see here is a cross-section on this graph, and the dots are the data and the lines is the theory, which means that we really understand what we're doing. So we really understand how this interaction comes about, and we can really extract the charge from the surface acoustic wave with the SET. Let me mention that we really stumbled on this. We wanted to do something completely different, but when we saw this, we realized that, wow, this is something that we can really do. And so this is a perfect example of progress by mistake. So you can ask yourself, well, how much is the displacement sensitivity? In our device here, we had a charge sensitivity of 25 microelectrons per square root of hertz. This is not the best SET we've had, but on this, it's still a pretty good charge sensitivity. Now, you know how much displacement gives how much charge. So it's this amount here, which you can easily calculate. And so that gives us a displacement sensitivity, which is actually very, very high. With this device, we can sense displacements which are 30 attometers per square root of hertz. The only thing that is better than this is the LIGO for gravitational waves, but that is measuring at much, much lower frequencies. This is measuring at 1 gigahertz. You can compare this to the quantum limit, and in fact, the quantum limit is still quite a bit away from this number that we measure. Nevertheless, this is a very high sensitivity. So here's the first experiment. What we do is we send in a very short pulse on this IDT here. So the wave comes here, it comes to the SET, and we see a pulse here. And note here that here is where we send in our pulse, and nothing happens at first because it takes time for the surface acoustic wave to reach the SET. And this time, by the way, fits perfectly with the sound velocity and the distance between the SET and the IDT. Now, then it passes on and gets reflected here and comes back. And you see this is the second peak that we see. Then when it goes back on this side here, some of it is actually converted back into the electromagnetic domain, and only a portion of it is reflected. And when it comes back, it has a much lower amplitude. And then you see the next reflection and so on, and here you can even see reflection 5 and 6. Another thing you can do is you can send in a long pulse, and then after a short time, you get the first response, when the wavefront hits the SET. Then when it reflects, it comes back, and then since it's a long pulse, it interferes with the previous pulse, or the trail of the pulse. And if that interference is positive, this signal starts to ring up the surface acoustic wave cavity. And you can see we don't have a very high finesse in this cavity, but nevertheless we can ring up that cavity. And then we can ring it down again like this. If we change the frequency just slightly so that the reflected wave is out of phase with the trailing wave, in fact, then you see that here the signal subtracts instead. And you can see it's trying to ring up, but it doesn't succeed because it's always out of phase. We can also do this more arbitrarily, so sending in a pulse which is 2 microseconds here, we get a very complicated pattern as a function of time and frequency. And I show this just to illustrate that we understand what's going on. This is the theory, and we can fit these two pictures quite nicely together. Using the parameters from this fit here, we can also reproduce the frequency behavior of the IDT quite nicely. The last thing we did here in this experiment was to turn down the knob on our microwave source. So now we're sending less and less phonons in this pulse. And here we have turned down the content of the pulse to only 1 phonon. So the energy that passes in this pulse underneath the SET is only 1 phonon. So h bar omega. And you can see that here we actually can detect that if we average for quite some time. So we need to average about 1 million times to get resolution for a single phonon. But this experiment really told us that it is possible to generate pulses containing just a single phonon, and that there's a possibility to detect it and to interact with it. So therefore we designed the next experiment, which is what I'm going to tell you about next. The first thing to realize is that this transmon qubit actually looks pretty much like an IDT. And so it should be possible to have a sender IDT here and make a receiver IDT into a qubit. So by coupling 2 Josephson junctions to this IDT, we actually make it into a transmon qubit. And then we should be able to measure reflection and transmission from this device. So here is the sample that we have measured. Here is an IDT. It generates SAW, and it can send it to this IDT here, which has 2 Josephson junctions here. So this is the qubit. So we can send in signals here. We can look at what gets reflected and comes out here, and then we can detect that with the amplifier. We can also apply a gate here so that we can excite the qubit electromagnetically. So we have the possibility of talking to this qubit both acoustically and electromagnetically. So you see we have 3 controls. We have the SAW wave, we have the gate signal, and we can also change the magnetic flux in this qubit so that we can turn the qubit frequency in or out of resonance with the frequency of these 2 IDTs. And now we use a higher frequency, so now we're at 4.8 gigahertz. All the information we extract we get from the acoustic signal, and everything of this is at 20 millikelvin. So here is the IDT, just a few numbers. This is aluminum on gallium arsenide. The number of fingers here is 125. The width here is 25 microns, and that gives us a frequency of 4.8 gigahertz because we put the finger spacing to 300 nanometers, which gives us half a wavelength. And combined with then the velocity of sound, we get 4.8 gigahertz. So here you see this finger structure here. The IDT we model as with a scattering matrix. So we have 3 ports. We have the electromagnetic port, and we have 2 acoustic ports. That gives us this scattering matrix here, and because of symmetries, there's actually only 4 matrix elements which are different that we need to extract. So one of the easiest things to extract is just the electromagnetic reflection here, so the S11 parameter, and that we measure here. You see this goes down to minus 6 dB, so this tells us that this S11 is practically 50%. So in other words, 25% of the energy or power is reflected directly, and 75% is then converted in the IDT, of which one part goes to the acoustic wave and one part is simply losses. The qubit looks like this. So here is a zoom up of that, and here you see the little squid, and the capacitance is now these finger capacitors of the IDT. The unharmonicity of the qubit, so the difference between the 1-2 transition and the 0-1 transition, is about 220 megahertz. The coupling rate, so the relaxation rate through phonons, can be very easily calculated from classical arguments. So it depends on the number of fingers, the piezo constant of the material, and the frequency of the qubit, and we get, for this case, roughly 30 megahertz with only 20 finger pairs. So we could easily make this a lot stronger by having more fingers, but also by having a stronger piezoelectric material. We have done 3 types of measurements that I want to show you. The first one is where we do pure reflection. We just send in a signal, we look at the reflection from the qubit, and we detect what comes back. So this is acoustic in, acoustic out. The second type of experiment that I will show you is where we listen to the phonons coming out. Then we excite the qubit with the gate here, and it relaxes through phonons because it's much stronger coupled to the phonons than to the gate here, and therefore we have electric in and acoustic out, and we can listen to what comes out. The third experiment is where we do two-tone spectroscopy, where we drive both with the control and with the acoustic wave here, and so we have a combination of electric and acoustic in, and we have acoustic out, and we can look at the energy structure of the qubit. So here we have the result of the reflection. So this is the first measurement then, like this. So you see, first we have this loss of 6 dB. This is just the reflection from the IDT. But on top of that, we have these spikes here. And this is precisely when the qubit's frequency goes in resonance with this frequency here, which is the IDT frequency of 4.8 gigahertz. And so you see it comes repeatedly here. And we can model that with the scattering matrix. So the reflection is just given by this expression here. You note here that we have the pure reflection here from the IDT, and we have measured that. So in fact, we can subtract that from the data, and then we get the pure signal from the acoustics, or from the surface acoustic waves. And that makes it easier. But nevertheless, we can fit this data with this red line according to this expression here. So now we have subtracted the pure photonic reflection, and this is the signal which is purely acoustic. And you can see that this is where the qubit goes in resonance. Here is magnetic flux, so this is tuning the qubit, and here is the frequency. And so if I zoom in on one of these, you see that we have this response here as a function of qubit detuning or flux, and here the frequency that we apply. If we take a cross-section of that, you see that here we have a Lorentzian peak, which we can fit very well to the data, and from this we can extract the coupling to 38 megahertz. This should really be gamma over 2 pi, by the way. We can also take the peak value here and look at how does that change with power. It changes like this. So this is the acoustic reflection as a function of power. And you can see that here we really see this nonlinear reflection of the qubit. Very similar to what we saw before of nonlinear reflection of the photons in an open transmission line. And you see that also here we get a nice fit with the same parameters as in this one here. The next thing we do is that we listen to the qubit. We send in a signal to the gate, so the qubit gets excited, then it relaxes through phonons, and half of the phonons come out this way, which we don't see, half of them come out this way, and those we listen to. And here you see this is the magnetic flux, so the detuning of the qubit, and this is the power we send in. And you can see here that along this line here, we really have this nonlinear reflection. But we also have more features here. And this, so you see here we have one feature, and here we have another one. You can even barely see one up here. And this is multi-photon transitions, where we use 2 photons to go from 0 to 2, and then we have a cascade of phonons coming out at these 2 frequencies, and that we see here. This peak here is when we excite to the 3rd state, and so on. So we can use these multi-photon transitions to actually extract the parameters for the qubit very accurately. So you see that we can fit this to theory quite well. This is the experiment, and this is the theory, and there's an obvious agreement between the two. And this is using the same coupling rate that we had before. By the way, in all our fitting, we assume that pure dephasing is actually very small. So you can say that's a result of our fitting, that the pure dephasing is actually substantially smaller than the coupling rate to the phonon degree of freedom. Looking at these multi-photon peaks here, we can compare when we're at negative flux here and at positive flux. So the qubit is the blue line here. It moves like this as a function of flux. But if you then look at the multi-photon transitions, they should be at these frequencies here. And by fitting these crossings here with the positions of these here, we can get a very accurate value for the Josephson coupling energy and the charging energy of our system. So these are quite accurate with small error bars. Now, you could argue that maybe this is just a crosstalk signal. So are you really sure that this is an acoustic signal? And yes, we are, and because we can see this in the time domain. By sending in a pulse to the gate here, we can compare if there's some crosstalk, and there is some crosstalk. That's the signal you see here. So this is the pure crosstalk signal. But and this is taken when the qubit is taken off resonance, so there's no acoustic signal at all. But if we then turn the qubit into resonance, we also have to add the saw wave here. And you can see that there's sort of a stepwise increase of this signal, and even more evident, it's clear that there's a stepwise decrease of this signal. So this is when the acoustic signal comes on. You can also change the frequency of the qubit just slightly so that the bouncing of the phonons back and forth here is out so that the interference is destructive. And then you can see that here first we have the crosstalk signal, but then we subtract with the acoustic signal. And it stays low, and then when we turn off the crosstalk signal, you see it comes up back again. So that really proves that there was phonons in the cavity bouncing back and forth. So this tells you that the time of flight here is 40 nanoseconds, which agrees well with this distance here. And it also tells us one of these other matrix elements, namely what is the coefficient for bouncing at the IDT here. We can also do this with a lot shorter pulses, and you see here is the crosstalk signal. Here is the first phonon pulse after 40 nanoseconds. When this signal goes here, it bounces, comes back, bounces, and comes back here. So this is a triple transit, and that comes 80 nanoseconds later. And you can even see the 5 times transit here in this peak. So this is clearly an acoustic signal. The last thing I'm going to show you is the two-tone spectroscopy. So here is where we send in an electromagnetic wave on the gate, and simultaneously we send an acoustic wave on from the IDT here. And you can see here that we have some structure here, and we can actually explain this structure here. So if we look at this feature here, this is when we're just sending in surface acoustic waves on resonance with the qubit at 4.8 gigahertz. So that changes the reflection slightly. If we look at this feature here, this is when we have the qubit at the same frequency, but we're actually driving with photons on the 1-2 transition, so we're Rabi splitting these two levels. So you can say that this is an Outler-Towns splitting here that is probed by acoustic waves. And the last one here is when you do, when we have changed the qubit frequency, so now the 1-2 is at 4.8 gigahertz, which is the one that we can listen to, and by then pumping here at 5.02, we can populate this line, and therefore we see reflection also from this level here. And we can do this for a number of different powers on the gate, and you can see that the experiment and the theory agrees quite well. We see a very similar structure in the theory as we do in the experiment. This theory here has to include up to 6 levels to make this fit. 6 levels of the qubit. So at the end, I would like to tell you, why is this interesting at all? You could argue that, well, photons are much more coherent than phonons, so why would you bother doing something with phonons? And there's a number of arguments, and the first one is really related to the slow speed of the sound. So this is 5 orders of magnitude slower than speed of light. So that means that you have time to do things on chip. If you send a pulse from one side of the chip to the other side of the chip, you actually have time to do things in between, because it takes a number of microseconds, even up to milliseconds if you have a long chip. It means that you can do things like this. You can have a qubit here which is on resonance, so that the pulse that comes in here would be reflected. But during the time it's being reflected and bounces back, you can actually close another qubit behind it and sort of catch a phonon in flight between 2 qubits. So that would be an interesting experiment to do, and that it would be very hard to do with photons because they're simply so fast. Another thing that's interesting is that you can make long atoms. Yeah, okay, so here your phonon is trapped. Yeah. The other thing you can do is that you can actually have atoms which are much longer than the wavelength of the quanta that you're looking at. If you think about ordinary atoms, typically the wavelength is much longer than the size of the atom, maybe with the exception of Rydberg atoms. But so what you can do then is that you can send in a signal, but if your atom is really long, you can think of sending in a pulse, which is actually shorter than your atom, and you can then do some manipulation on the atom during the time of flight. So you can say detune the frequency of the atom while your pulse is passing, and that would be a new regime which I believe has not been explored neither experimentally nor theoretically before. It's also interesting to note that because our speed of sound is so much lower, our wavelengths are actually the same as for optical light. So there should be possibilities to actually couple optical light with these surface acoustic waves. And that's an interesting opportunity if one can make a coherent interface between microwaves and optical photons. And last, but maybe not least, is that the piezoelectric coupling may allow much stronger coupling than what is possible with photons, because we can add the number of fingers. We can have, we had 20 in this case. You can add many more if you like. But also we can go to a much stronger piezoelectric material like lithium niobate, which is actually 80 times stronger than gallium arsenide. So we could easily get up to gigahertz couplings, and maybe we can even approach the ultra-strong coupling regime. So let me summarize and give credit to the people who did this. So on the photon side, I've shown you that we can have very high extinction from an artificial atom. We can demonstrate electromagnetically induced transparency in outlier town splitting. We use the outlier town splitting to show a photon router with a 99% on-off ratio and a 10 nanosecond operation speed. I also show that we can have anti-bunching, so we can get non-classical microwave states using just reflection from this qubit. And I also show that we have very large cross-Kerr effect. On the phonon side, I showed you that we can detect displacements with very high accuracy using SETs. And we can even detect pulses containing one single phonon. I also showed you that we can do this nonlinear reflection of phonons from the transmon qubit, very similar to as what we did here with photons. And we can listen to the emitted phonons, and we can also do two-tone spectroscopy, and it seems to agree very well with theory. So the people who did the photon stuff, this is Yu-Shun Hoi. You see he's the first author of all these 3 papers. Chris Wilson was also a very important person in this photon things. Here on the phonon side, it's really Martin Gustafsson who has been the main person. And in both cases, we've had very good theory help from the group of Göran Johansson and his students. And in several aspects of this, we have also collaborated with the University of Brisbane, Madrid, and Paul Drude Institute in Berlin. So with that, I thank you for your attention.